Okay. So I'm going to share my iPad screen with you guys again. And we're going to do some calculus applied to kinematics. All right. Here we go. So do copy this down if you've got the time. If you haven't got the time and you don't get it all down, you can hopefully then you can come back and watch this again, watch it back, and then you'll be able to make sure you get everything down. So this is displacement, velocity, acceleration. And it's calculus, which is integration differentiation, but applied to kinematics. So the kinematics is the displacement, velocity, acceleration, things moving, you know, traveling distances, moving at speed, accelerating, changing their speed. So objects, particles, planes, bikes, motor cars, whatever it is, we're going to be describing them. We're going to be using calculus to find different things about them. So the first thing is we have to have imprinted in our brain is the kind of connection between displacement, velocity, acceleration. And I have shown you this a few times, and I really hope everybody knows this, but I'm going to write it down again. So if we have a displacement, that's a distance. If we have a velocity, that's kind of like a speed with a direction. So these are all vectors. They're all actually, even displacement is a vector. It can be positive, can be negative. If we assume like height of 0, you could go up or you could go down. So that's displacement. Velocity is similar. You could be traveling forwards or backwards. Could accelerate, you could decelerate. So that's positive or negative. They're vectors. But we will be considering generally motion in one direction, and they'll be changing over time. So displacement measured in meters, velocity is measured in meters per second. So that's a rate. So that's how is my displacement changing. So I differentiate displacement to get velocity. Now acceleration is meters per second per second. So that's the rate at which my velocity is changing. So again, I will differentiate to get acceleration. And of course then, to go the other way, I must integrate, because integration and differentiation are opposite. So you have to know that. That has to be burned into your head. Don't integrate when you should differentiate, and don't differentiate when you should integrate. And of course, when we'll be integrating, we'll need to consider our constants of integration. So going that way is always harder. And pretty much all of the questions on this topic that Cambridge ask, the vast majority of them will be integration, okay? It's not always the case, but most of them are integration. So we will need to consider that plus C, and in certain cases, you'll have to find it. Sometimes it turns out that it's 0, all right? Okay. So I've got a question here, so let's have a look. Okay, hopefully you can all see that. So we've got an airplane. It's moving along a horizontal runway before it takes off. Starting from rest at O. So that's a crucial bit of information right there. Starting from rest at O. So I'm going to kind of underline that. And it has a speed 90 at the instant it takes off. So that's another crucial bit of information. While it's on the runway at time t, after leaving the origin, its acceleration is given by that expression. So what that tells me is that the acceleration is not constant. So I can't use suvat, okay? Sometimes you would be trying to think, well, maybe I can apply suvat to a problem like this. But if we have a look at that expression, the acceleration depends upon t. It depends upon t, which means that for every second that increases, the acceleration is going to increase. If if that second part, the plus 0.012t, wasn't there, and it was just acceleration is 1.5, then it's constant, then you can use suva, yeah? But our acceleration is not constant, so we can't use suva, so it has to be a calculus question, it has to be an integration or differentiation. So part one, find the value of t at the instant the airplane takes off. So basically, like, how long does it take for the airplane to take off? Starts from rest, it accelerates according to that expression until it reaches a speed of 90, and then it takes off. So how long does it take for it to reach that speed of 90? So that's what we need to find. So our expression for the acceleration is a of t. It's a function of time. And it's, I'm just going to write it this way, 0.01 to t plus 1.5. So when t is 0, acceleration is 1.5, and then every second it increases by 0.012. Okay. So we want to know how long it takes before it takes off. We need to find v of t because we're given the speed at 90. So we know what the value of v of t is 90 when it takes off. So if we had an expression for v of t, we could set that expression equal to 90 and solve it to find t. That will tell us the time when the velocity is 90, which will tell us how long it takes to take off. Okay, so we need to know our hierarchy, right? We've got acceleration, we want to find velocity, so we have to integrate. So we have to integrate a of t with respect to t. So v of t is equal to the integral of a of t dt. And when you're solving integration problems, I think it's extremely important to be very rigorous, very meticulous, very slow and methodical, and don't rush. Do it step by step, and try not to do too much in your head, because that's when you start to make mistakes with things like minus signs or just small numerical errors which will cost you loads of marks. So do this as methodically and slowly and meticulously as you can. So we have our expression a of t is 0.012 t plus 1.5, and we're going to integrate that with respect to time. So the first part of that integral, this is just polynomial integration, right? In mechanics, you don't have to do any of the really hard integrations that you'd be doing in pure, like, you know, trigonometric substitutions or integration by parts. Like, it's just easy, and this is easy integration, so you should all be able to do this by now. So we integrate 0.012 t with respect to t. T goes to t squared, and we divide by the 2, so it becomes 0.006 t squared plus 1.5 t plus c. I have a constant of integration. It's an indefinite integral. I didn't integrate between any two velocities, but I do know it starts from rest. So if it starts from rest, that tells me that v of 0 equals 0. At time t is 0 initially, it has no velocity. So I can use that to find and show that this constant of integration here is 0. Basically, what the constant of integration is here is the initial velocity, right? If there was an initial velocity, that would be that constant of integration, because I'm finding an expression for velocity. That's easy to show, right? That the constant 0 if t is 0 because plugging in t just gets you 0. So now I know v of t exactly is, my expression for v of t is equal to 0.006 t squared plus 1.5 t. And at some time, that velocity will be 90. So at some value of time, the velocity is 90. And I want to find that value of time. So I set it equal to 90. I set this expression here equal to 90. T squared, 1.5t equals 90 at some value of t. I just have to solve that to find t. So this is a quadratic equation. There are lots of ways to solve these. You guys have been doing this for years, but even your calculators can solve them. So you can check them on your calculator if you've got it wrong. And just make sure you don't get it wrong by checking it on your calculator. I like to, if I can, factor these because usually they do factor, because it's usually like some nice value of time. It's not always the case. So to factor this, I would multiply or divide everything by 0.006 to get, I guess, what, t squared plus 250t, and I would take the 90 on the other side and divide it by 0.006 would be 15,000. Okay, and then I would try and factor that and solve it. This would be t plus 200. No, sorry, t minus 50. Do that one first. And t plus 300. Okay. Again, you could use the formula. You could complete the square. You could whatever. You could solve this. So then this tells me that t is either equal to 50 or t must be equal to minus 300. So obviously one of those solutions I can throw away, minus 300, because 300 seconds in the past, the plane wasn't traveling at that speed unless it's just come into land. I'm not interested in that. So 50 seconds, right? It takes 50 seconds for the plane to take off. Easy. All right. So part 2, find the distance traveled by the airplane on the runway. So this is how far does it go before it takes off. And again, it starts from the origin. So what that tells me is that, again, the constant of integration is going to be 0. It's not starting 10 meters down the runway. It's starting at 0, 0. So s of 0 is also 0, right? The displacement when the time is 0 because it starts at the origin. So that tells me that the next constant of integration will also be 0 without even having to kind of think about it. So it's really important that you think about when it says starting from rest at 0, you think through what does that mean? What does that tell me? It's telling you about the constants of integration. So part 2, let's do part 2. This is part 1. So part 2. The distance traveled. So now we need an expression for s of t. So again, s of t is displacement. We have to integrate velocity or integrate acceleration twice. Well, we have our velocity expression from before, so we can integrate that to find our displacement. So it's the integral of velocity with respect to time. So my velocity expression is here, 0.006 t squared plus 1.5 t dt. Okay. So we're asked to find the distance it's traveled along the runway, I can actually make this problem a little bit easier because I know the concept of integration 0, but I can actually make this a definite integral. I actually want the distance traveled from t equals 0 up to the time it takes off, which I've already found was t equals 50. So I can actually make this a definite integral and say I want the integral of velocity from 0 to 50, from a time of 0 to 50. Okay, so when I integrate this, I get the t cubed, t goes to the power 3, I divide by 3. 6 over 3 is 2. So, so I should get 0.002 t cubed, okay, plus 1.5 t squared, 1.5 t squared, all divided by 2. That's 3 over 2 over 2, which is 3 over 4, or 0.75. And it's okay to use decimals in mechanics. In pure, you'd maybe want to keep these things as exact as fractions. In mechanics, because the numbers are real world numbers, it's okay to use decimals just because they tend to be kind of like really big or small because they're trying to describe real physical things. And I need to evaluate that between from 0 to 50. And so then I just plug in my numbers for that. So we've got 0.002 times 50 squared plus 1.5 times, 50 cubed. It's 1.5. See how easy it is to make mistakes. 0.002 times 50 cubed plus 0.75 times 50 squared. Okay. And I think you should get, after doing that, 2,125 meters. And actually, my calculator can even do these integrations, so I can check on my calculator if I've done that right. Again, I would recommend doing that because it's so easy to make mistakes doing this. You think it's easy, so you kind of just write stuff down, and then if you don't check at each step, have I done that right? Have I done that right? You'll make at least 1 or 2 mistakes on an exam. Okay. Any questions? No. Okay. We've got about 5 minutes. I'm not sure how much of this one I'll be able to get through. So 5 marker for the first one. Same thing. Okay. We've got a particle P starting from rest at a point O, telling me the constants of integration. Moves in a straight line. Has acceleration that depends upon time. It's not suva. Time t, seconds after leaving O until t equals 10. Find the velocity and displacement when t equals 10. So what we've got is A of t is equal to 0.6 t. We want V of t, which is the integral of A of t with respect to t. And we want S of t as well. So let's find V of t first. Just integrate A of t, and we get 0.6 t squared over 2 is 0.3 t squared plus c. But I know that c is 0. Why? Because it starts from rest. So v of 0 is 0. V of 0 is 0. The constant of integration must also be 0. So this is just equal to 0.3 t squared. S of t equals the integral of v of t with respect to t, which is 0.3 t squared. So it goes to t cubed and gets divided by 3. 0.3 over 3 is 0.1 t cubed plus c. And again, I know that S of 0 is 0 because it starts from the origin. So that means that the constant integration, again, in this case is 0. It's not always, so you have to think about it every time you do it. So s of t is 0.1 t cubed. Now I need to know what is the value of the velocity and displacement when t is 10. Well, that's easy. I can just sub in 10 to find these. So I need v of 10 is velocity when t is 10 is 0.3 times 100 times 10 squared is 30 meters per second, and s of 10 is 0.1 times 10 cubed, which is 1,000 times 0.1 or 100 meters. Okay, easy. So tomorrow I'll be giving you some of these questions to have a go at yourself, and I might mix in some of the other questions where you can use straight lines and find the area under graphs instead of calculus. Okay, any questions? So that part 2, 7 marks. I'm not going to get this done in 3 minutes. After t is 10, it has a new acceleration minus 0.4 t until it comes to rest at point A. Find the distance OA. So if I want a distance, I need to find s of t, but I need to find v of t first. So let's find v of t quick as I can. So t squared over 2 is minus 0.2 t squared plus c. So what's the plus c here? The plus c is going to be, what was its velocity initially with this new acceleration? Well, that will be its final velocity from before, which was 30. So actually this is going to be minus 0.2 t squared plus 30. Okay, s of t. So we want to integrate our expression for velocity now, minus 0.2 t squared plus 30 dt. T squared goes to t cubed, so that's minus 0.2 over 3 t cubed plus 30 t plus c. Okay. Wait. So at t is 10, has acceleration of this until it comes to rest at point A. Find the distance OA. So it's already traveled at this time here, which was 50 seconds. It's already traveled 100 meters. So I want to know how far does it travel from then until coming to rest. And I've got less than a minute. So I don't know if I'll be able to do that, but hopefully I can leave that one with you to have a think about. I've done a fair chunk of it. Any final questions before we go? I'm going to make this whiteboard available to you so you can take some screenshots. Okay. All right.